3.2 and 3.3 are how to graph a function using calculus. So the idea is start using kind of all the ideas we had based on a derivative. Next week we'll also use the second derivative. And then how can we draw a really good graph just using some ideas about the field and everything else. All right. So we're kind of putting everything we have together to describe a function a little bit more clearly. And there's something in 3.1 we skipped a little bit. What is a critical number?
It's a place where it's either not continuous or it has a zero.
Yeah, almost. So x equals c is a critical number of f. Yeah. So there's kind of three things we need. There are two things, I guess. One, c is in the domain. So we only care about x values in the domain of the original function. So it's in the domain, and then f prime of c is equal to 0, or f prime of c is undefined. So when you mention not continuous, if you're not continuous at a point, then your derivative is undefined. So that would fall into this category. All right. So why do we care about critical numbers? Well, the big goal that we want to talk about is when do we have a relative max or relative min? Starting in 3.4, we'll talk about a global max, global min. So, kind of think about 3.4. Say you know your profit function. You have a company, you have a profit function, you know how much profit you make if you produce and sell a certain number of units. What's your goal? Make the most amount of money. You want to maximize your profit. So what do you need to do that? You need to know at what x coordinate, how many units should I produce to make the maximum profit? And hopefully that's a positive number. All right. So in sections 3.2 and 3.3, we take a step back. So in 3.4, we'll say what is the biggest value possible? What is the maximum? What is the minimum, the smallest value? In this section, we want to talk about local extrema. This is a little bit in 3.1 also. So extrema is just saying max or min. Instead of saying max or min, just one word for both. So say your graph looks like this. What does it mean to be a local max? It's really saying it's the biggest y coordinate around. So like this y coordinate's not the biggest one, right? The biggest one would be, looks like right here, except that goes up forever, so there is actually no max on this. What about a minimum? The minimum would be right here. But then locally, that's a minimum. So this is where your book's a little bit different than some. We would call that a local max. It's an endpoint where if I move this way, I'm undefined. If I move that way, I get smaller, right? So it's the biggest y coordinate right there. And then somewhere up here, looks like I have a local max. Down here, looks like I have a local min. And then right here, it looks like I also have a local min. What happens to my derivative here?
It'll be like, it'll jump up.
At this one, do I have a derivative? No, when you have a cusp or corner, you don't have a derivative. What about here? Yeah, what's my derivative value? 0, where it levels off. What about down here? Same thing, f prime is equal to 0. So this one's a little bit of an outlier. Technically, this one, f prime is negative. So one way we can find local extrema, if you're on an interval a to b, so let's say it's an open interval. I drew the closed interval case just to kind of highlight a separate point. But say you're on an interval a to b, local extrema occur at critical points. Does that make sense based on our graph? What has to be true at a local extreme value? If it's the biggest coordinate, and I'm somewhere on AB open, I'm somewhere in the interior part, so I'm ignoring endpoints. Endpoints, you can have a big value and your derivative negative. That one's kind of, all bets are off. It depends on what happens at that one point. So that's a little bit of a different story. That's one we'll talk about more in 3-4. But anywhere else, if I want a local min, I need to go downwards and then upwards. It must turn around. If I want a local max, I must go up and then down. It must turn around. What happens to make my graph turn around? What would have to be true? My derivative would either need to be 0 or undefined. So if we find all the critical numbers, we know all the possible places for local extreme. Now I could have something like this. Is that a local max or min? My derivative is 0, so it's a critical number, but it's not a max or min because if I move this way, it gets smaller. If I move that way, I get bigger. So you can have critical numbers that aren't a max or min. That's fine. But if you have a max or min, it must be a critical number. So the idea in 3.2 and 3.3, how can we find all the relative maxes and mins without doing way too much work? And then you end up with what's called the first derivative test. Where would this be relevant? We know if we have a max or min, it must be a place where my derivative is 0 or undefined. And then how can I characterize that I have a max? My graph went up, and it went down. My derivative must be positive and then negative. For this min, my derivative must have been negative and then positive if I went downwards and upwards. Does it matter that my derivative is undefined at that one point? No, all that matters is it was decreasing then increasing. Derivative was negative and then positive. Right. So how can we find all the maxes and mins, or the relative max mins? We need the critical numbers, and then if you're seeing the critical number, you decide, was my derivative positive and then negative, or negative and then positive? All right. Ends up, that process is what's called the first derivative test. How do I decide if a point is a max or min? I can do the first derivative test. Did my derivative go plus and then minus, positive then negative? If so, that meant I was moving upwards, and as I started moving downwards, I must have had a maximum. All right. So the idea in this section is, can we use the first derivative to tell us more information about the graph? What kind of graph, what kind of information can we get? The big one is increasing or decreasing. If my derivative is positive on an interval, I'd say I'm increasing. My graph is moving upwards. If it's negative, I'm decreasing, I'm moving downwards. And then if I want to find what are my relative maxes and mins, I can use the first derivative to answer that question. So, as an example, let's say we have f of x is e dx over 1 plus e dx. Anybody know what the graph of this looks like? When you're in pre-cal, you have things like rational functions, so like x over 1 plus x. But you never just randomly throw in exponentials, right? As far as we're concerned, it's all about the same idea here. So, first part, when is this increasing slash decreasing? I want to find intervals where I'm increasing, intervals where I'm decreasing. What does it mean to be increasing? For us, it means the derivative is positive, or the derivative is negative for decreasing. So, before I go too far on this, what's my domain? The book never asks this. I always start with what's a domain for this. Why is that one relevant? We said all the information is, or anything with critical numbers, you must be in the domain. So, how would I get the domain here? What could go wrong? Yeah.
1 plus e dx can't equal 0.
I need that to be true. divide by 0. Does that ever happen? Is e to the x ever equal to -1?
Mm-mm.
No. So I'm good here. My domain is all numbers. So I don't have to worry about any random domain issues. That's usually the place where you want to be a little more careful and check at the beginning. Because then anything that you throw out of the domain isn't a critical number. Why would I say that? If I have a number that's not my domain, is the derivative defined there? No. If my function doesn't have a value, my derivative definitely doesn't have a value there. So anything not in my domain, I would get f prime is undefined there. Is it a critical number? No, because it wasn't originally in my domain. So that's where you always want to find the domain first so you know which numbers to throw out and not consider. Alright, so how can we decide increasing, decreasing? I want to know, when is my derivative positive or negative? So first we need to find the derivative. So from that, I guess I need to do the quotient rule. Bottom times derivative of the top, minus the top function, what's the derivative of the bottom? Just easy x. Divided by bottom part squared. So I get what? If I factor out e to the x, I'm left with 1 plus e to the x minus e to the x over this. So I end up with, let these cancel, so I just get e to the x divided by 1 plus e to the x, all squared. Alright, so I know my derivative. Do I have any critical numbers? How can I decide? So if I want to know, you have to go back a long ways. How did we decide when a function is positive or negative? We did this back in 1.4, which means nobody remembers it. We would draw a number line. So here I'm going to label it f prime. Really what we want to do is we just want to mark the critical numbers on the number line. So when can I change from positive to negative? This is actually back to what's called the intermediate value theorem. If I have something that's positive and now it's negative, what happens? You have to go through 0? Or it's undefined. So if my derivative is either positive or negative, or I need to know when is it, or I need to know all the places it could change. When can it change? Only if I'm 0 or undefined, which is also similar to how we find critical numbers. All this is somewhat related. So when is f prime of x equal to 0?
When the numerator equals
Say the
0.
top's equal to 0, so never happens. E to the x is never equal to 0. What about the bottom? Or what about when it's undefined? Doesn't mean my bottom part is equal to 0, which again never happens because e to the x is never -1. So what does that mean? I have no critical numbers? Alright. Find any critical numbers. How can I decide if I'm increasing or decreasing? Yeah. Why do we do this? This says I can only change at a critical number, basically, and I have no critical numbers. So that means if I'm ever positive, I'm always positive. If I'm ever negative, I'm always negative. So what can I do? Just plug in one number. So let's say we plug in 0. What do you get when you plug in 0? 1 over 1 plus 1 squared, which is a positive number. Here's the nice thing, you actually don't even need to know the exact value, you just need to know positive, negative. Since that's positive, my derivative is always a positive number. I only need to check one number because it can't ever change. If it was going to change, I'd have to get 0 or undefined. All right. So my derivative is always positive, so when am I increasing? I'm increasing whenever my derivative is positive, right? So I'm gonna be increasing on the interval -infinity to infinity. Am I ever decreasing? No, because whenever we got a negative sign. Alright, so I'm always increasing, never decreasing. What would a graph look like? No. What else could I say? First I was asked about increasing, decreasing. Next I could ask about relative extrema. Do I have any relative extrema? No, I'm always increasing. To get a max, it'd have to go plus and minus, increasing and decreasing. To get a min, I'd have to change. Because I'm always increasing, I have no relative extrema. So what does my graph look like? If I don't do any work, because this was positive, let's say my function is always moving upwards, right? It's not wide enough information, so I know it's always going upwards. When we get into section 3.3, we can actually draw a better picture. We can talk about, is it curving upwards or downwards? So we get a little bit, here I can just say it's going upwards. But I can do a little bit better and look at index. So if it's going upwards forever, does it go up to plus infinity, or does it level off? If I'm moving this way, it's moving downwards forever, right? If I'm moving the opposite direction, does it go down to negative infinity, or does it level off? So that's when we talk about end behavior. I want to find the limit when x goes to negative infinity, and the limit when x goes to plus infinity. So how can I find this limit? When I go to negative infinity, what do I get? What's e to the negative infinity? E to the x looks like this. So if I go off to negative infinity, my y coordinate is basically 0. I know it has a horizontal asymptote of y equals 0. So this would be 0 over 1 plus 0, 0. What about this one, when I go to plus infinity? Infinity divided by infinity. So what can I do? I do left house roll? Like I said, there's a reason we went ahead and did that one. E to the x over e to the x is 1. See, all these limits you have to take in 3, 2, and 3, 3, you have a shortcut now. Alright, so what's the graph look like? If I go off to the left, I go to 0. If I go off to the right, my y coordinate gets close to 1. And I'm always increasing. The only option is something that looks like this. Did we even plug in a single number? We plugged in one number to figure out the derivative was positive. And you have a very accurate looking graph actually. So the goal when we graph in here, you will plug in like 5 numbers and have a good graph, which is completely different than what you used to do. You used to just plug in a lot of x coordinates, get a bunch of y coordinates, try to connect the dots. Our goal is find the most important x coordinates to plug in and only use that information. If I know all the relative maxes and mins, if I know where I turn around, what happens in between, it just follows the pattern, right? So we're figuring out what's the pattern this graph must follow, and then we can draw the graph. We only need 1 or 2 pieces of information to draw a graph here. Any questions on that one? We have a bunch more of these that we're gonna do over the next few days. The graphing is more involved than most of what you end up doing. But I want to go ahead and start with that with the contract. Alright, so let's do this one last example today. Now I want to draw the graph of a function that has these properties. So when we're nice, we give you the number lines, so that people don't always think that. Otherwise, the first thing we have to do is actually find the number lines. So I always put zeros in there. The book won't write a zero. If they don't write anything, they just assume you know it's zero. But I always like to label them zeros. So let's say we know this about our graph. What does this say? It says when my function is positive or negative, and it says when it's increasing or decreasing. Why do we do the number lines? It's so we can decide increasing, decreasing. So if I had all this information, instead of trying to find it all myself, what are my critical numbers? Yeah, anywhere f prime is 0 or undefined, so x equals 0 and -1. Anytime we give you these, or we just give you f of x, pretty much the first thing you're going to do for every problem is come up with number lines. And why do we want number lines? They actually incorporate almost all the information. When am I increasing? -1 to 0, anywhere my derivative is positive. When am I decreasing? Yeah, 0 to infinity. Where do I have a relative max? Yeah, right, first time. So, what does my graph do? We must go this way, this way, this way. So where do I have a relative max? Must be at this one. Where do I have a relative min? Must be here. Like by the time you have a number line, you know everything about increasing, decreasing, relative max, relative min, all of that. All the problems we end up solving the same way. We draw number lines. Right? Why are we doing number lines? We need to decide when it's positive or negative. So if you go all the way back to 1.4, there are also videos on this. How do you decide when your function is positive or negative? And we talked about the intermediate value theorem and drew number lines. It's really just a build up to this. Now we're actually going to use that skill. So what does this graph look like? This says if I plug in 1, I get 0. And my graph must be decreasing. Or x equals 0, my derivative is undefined. And then x equals -1, my derivative is 0, but my graph is positive, right? So I have some point here where my derivative is 0, but I'm above the y-axis. Why am I above the y-axis? Because this says my graph must be positive. So I cross from positive to negative here. Here I'm above. I know my derivative was 0 there, and then it switches to negative. So here my derivative is negative, but levels off to 0. And then what would it mean if it's undefined? It could be something like that. It doesn't have, it's not going to level off to 0, it can have a corner. So anywhere it does not exist, you get a corner, you can get anything like that. I know it's not a vertical asymptote because this says 0 is in my domain. I get a positive number when I plug in 0. So there must be some y-intercept here. Does that follow this pattern? Down, up, down? And then you just make sure at this point my derivative is 0, at this point my derivative is undefined. Next week we'll add in a third double line for the second derivative. And the reason we do that, when I know a second derivative, it would actually tell me my shape is like this. So it's not only moving downwards, it's bending this way. Or it could be going like this, moving downwards but bending the other way. So it'll give us the shape part. And then we put it all together and we get really good looking graphs plugging in like 5 minutes. So that's where we're headed for next week. And we're going to do a lot of this.